Hi everyone, welcome to Unit 24 of online course on probability distribution. In this session, we are introducing a new distribution, namely negative binomial distribution. And here also, we are actually discussing the distribution with respect to a sequence of Bernoulli trials, that is modeling a random variable based on the Bernoulli trials. Consider a sequence of independent trials, Bernoulli trials, and we know there are two possible outcomes in a Bernoulli sequence of trials, say success and failure, and probability of getting a success, let it be denoted by P, remains the same from trial to trial, and the complement of the probability, that is probability of getting failure, is represented by Q, which is equal to 1 minus P. So, this is the Bernoulli sequence of trials. Earlier we have described binomial distribution, and earlier we have defined the geometric distribution. In all these cases, we are performing Bernoulli trials and modeling different situations. In the case of binomial distribution, we are modeling a random variable x, which is the number of successes obtained out of n trials of a Bernoulli sequence of independent trials. In the case of geometric distribution, we are performing Bernoulli trials until a success is obtained, and we are modeling a random variable x, which is the number of failures preceding first success, and that is the geometric distribution. And in the case of negative binomial distribution, what we are doing here is we are considering a sequence of Bernoulli trials, and that are performed until the occurrence of R number of successes. In the case of geometric distribution, we are performing Bernoulli trials until a success is obtained. But here our aim is to obtain R number of successes. And suppose we are interested in finding the probability of X number of failures preceding Rth success. Then this random variable is modeled by a distribution which is called negative binomial distribution. Let me repeat once again. Suppose we are performing Bernoulli sequence of trials until R number of success, a specified number of success is obtained. And let us define the random variable x as the number of failures preceding Rth success. Then x is modeled by the distribution negative binomial distribution. So, let us consider the situation. So, that is, we have the Bernoulli trials, a sequence of independent trials with a probability of success P, and we have only, in the Bernoulli trials we know, we have only two outcomes, success and failure. And we are performing this Bernoulli trials until we have an R success. Suppose this is the Rth, suppose we have Rth success is obtained somewhere here, and in previous trials we have R minus 1 successes So, we have r minus 1 success in the previous to this trial. This is a particular trial. Suppose this is the x plus rth trial. Suppose this is our x plus rth trial where rth success is obtained. And before that, starting from here, before that we have r minus 1 success, and of course we have x failures. So, consider this is x plus rth trial, and that trial resulted rth success. So, before the previous trials, we have r minus 1 successes and x failures. So, what is the probability of x, that is number of failures preceding r successes? In the case of geometry distribution, we are actually modeling a random variable x, which is the number of failures preceding first success. Instead of that, we are modeling a random variable x, which is the number of failures preceding r successes. And the situation, just look the situation here. In the before the x plus rth trial, how many trials are there? We have x plus r minus 1 trials. So, in this situation, we have x plus r minus 1 trials. And in the x plus r minus 1 trials, we have r minus 1 success and of course x failures. So, in the x plus r minus 1 trials, we have r minus 1 success and x failures. And what is the probability of that case situation? That is, probability of x is equal to x, that means probability of x failures preceding r successes. So, again once more, in the x plus r, this is x plus rth trial, and before this x plus r minus 1 trials we have, and in this case we have x failures and r minus 1 failure, r minus 1 successes. So, that are possible in x plus r minus 1, r minus 1 combination, that is in the x plus r minus 1 trials. These are x plus r minus 1 trials. We have r minus 1 successes are obtained in different combinations, and different ways are x plus r minus 1 c r minus 1, and the probability of getting success is p, and so r minus 1 success will be obtained p power r minus 1, and the failures are x. Okay. So, the probability of getting x failures and r minus 1 success is x plus r minus 1 c r minus 1 p power r minus 1 q power x, and this is fixed. This is actually the success. So, what is this probability p? So, actually probability of getting x failures preceding r successes is same as x plus r minus 1 c r minus 1 p power r minus 1 q power x into p, or that is equal to x plus r minus 1 c r minus 1 p power r q power x. And remember, x have any value 0, 1, 2, etc., and p plus q satisfies the relationship p plus q is equal to 1. And this probability model, that is probability of x failures preceding r successes when we are performing Bernoulli trials, with the probability of success P is given by this expression. And this probability model is the negative binomial distribution probability mass function. So, this is the concept behind the derivation of the negative binomial distribution probability mass function. So, here you will just look what is the basic difference between the binomial distribution and negative binomial distribution. In the case of binomial distribution, what we are doing? We are performing n number of trials and count the number of successes obtained out of n trials. So, that is, we fix the value of trials, n is fixed, and you are counting the number of successes, and that will be r, and though probability of x is equal to r is given by the binomial distribution probability mass function. So, in a binomial distribution, we have fixed the number of trials, but in the negative binomial distribution, we have fixed the number of successes. Why? Our aim is actually finding the probability of x failures preceding r success. So, r success, the number success, r value is fixed. So, in a negative binomial distribution, number of successes is fixed, but in the binomial distribution, number of trials is fixed. So, this is the basic difference between the two distributions while modeling the random variable, that are related with the Bernoulli sequence of trials. So, this known as negative binomial distribution because it models the number of failures unlike the binomial distribution. So, actually when we are modeling binomial distribution, our aim is modeling number of successes, but here we are modeling number of failures preceding r successes. So, negative binomial distribution models the failures that occur before a specified number of successes. So, let me repeat, negative binomial distribution models the failures that occur before a specified number of successes. Let it be suppose 10 successes. What is the probability of getting 10 successes, 10th success, and how many failures before the 10th success. So, that type of situations we are using by negative binomial distribution. So, these are the cases that I have already mentioned to you, that is, when we are performing Bernoulli trials, these are the events we have. Suppose we have R is fixed, number of success is fixed, so R times S. So, this is one of the events. So, if this is how many failures? 0. Suppose all first R trials resulted in successes, number of failures preceding the first success, R success is equal to 0. And second case, ER plus 1, here one failure and R successes. So, in different combinations, see different combinations like this. So, R times successes and one failure, and not that the last trial should be a success. So, always we stop the Bernoulli trials until R success is obtained. So, the last trial always a success. So, if this is the situation, number of failures is what? 1. So, you continue like this. Here the R times we have success and X time we have failures. So, if this is the situation, number of failures is X. So, that is, if we have the events ER plus 1, ER plus 2, etc. up to ER plus X, ER plus X, ER plus X plus 1, etc. Then the value of the random variable X, which is defined as number of failures preceding R success, are 0, 1, 2, 3, etc. And that is modeled by this is the case I have already mentioned. That is, probability of X is equal to X is equal to probability of X failures preceding R success. That means probability of getting R minus 1 successes in X plus R minus 1 trials and a success in the X plus Rth trial, because the last trial should be a success. And I have already given this probability mass function. One thing you note here, you have the NCR and NCn minus R are equal. So, using this expression, we can write X plus R minus 1 C R minus 1 in another form, X plus R minus 1 C X P power R. So, both models or both expressions, X plus R minus 1 C R minus 1 P power R minus 1. So, this is actually X plus R minus 1 P power R Q power X. And this expression, or X plus R minus 1 C X P power Q X. Both expressions are used as the probability mass function expression of a negative binomial distribution. Remember, the random variable X have the values 0, 1, 2, 3, etc. and P plus Q is equal to 1. And the probability mass function values, suppose we are making that as a graph. The shape of the graph is something like this. That is, when R is having different values, the shape will be different. So, this is the usual shape of the negative binomial distribution with the parameters R and P. An example, just you note, suppose we have a fair coin that is tossed until we get our fifth head. Suppose we fix the number of heads as 5. We are aiming to get 5 heads, and so we are performing the tossing of coin experiment until a fifth head is obtained. So, when we have the fifth head, suppose we are performing the experiment, first trial, second trial, third trial, etc. Okay. So, we stop the experiment if this is the fifth head. If that is a fifth head, we stop the experiment. So, before this we have 4 heads and X tails. So, suppose this is suppose we have X plus Rth trial, X plus Rth trial, and that is our fifth head obtained. So, before that we have 4 heads and X tails. So, that means probability of X is equal to X. Earlier we have the general model is what? X plus R minus 1 C X P power R Q power X. This is the general value. So, here it is R is equal to the number of successes fixed, that is 5. So, X plus R minus 1, that is X plus 4 C X, and P power 5 Q power X. And since it is an unbiased coin, the P and Q are equal, and that are equal to 1 by 2. So, representing this probability mass function, probability of X is equal to X is equal to X plus 4 C X P power 5, that is 1 by 2 power 5 into Q power X, that is 1 by 2 power X. So, combining we have 1 by 2 power 5 plus X, where X is equal to 0, 1, 2, 3, etc. So, this is a simple example which is modeled by the negative binomial distribution. Example, just consider, suppose a candidate is writing an examination with the multiple choice questions, and his probability of attempting the question with the right answer is 60%. That is, probability of answering question correctly is 60%. That means 0.60, the probability value. What is the probability that he gives the third correct answer for the fifth attempted question? That is, he is trying the examination by answering the questions, And what is the probability? The problem here is, what is the probability that he or she gives the third correct answer for the fifth attempted question? So just look here, what is fixed here? Our success is fixed. What is the probability that he gives the third correct answer? So R is fixed as 3. And that should be in the fifth attempted question. That is, how many failures before that? 2 failures. So we have 2 failures, and that is, we have the fifth attempted question. This is actually the third one. Here it is, and we have this is at the fifth attempt. This is in the fifth trial. In the fifth trial, we have the third success. So that means in the 4, 3, 2, 1 trials, we have how many successes? 2 successes. And how many failures? Of course, 2, because 4 trials are there. So we have x plus r minus 1, that is 4, C2, and that is, and p power r. P power r is equal to 3, so 0.60 power 3, and q is 0.040 power 2. That is equal to, simplifying, we have 0.0207. So this is an example, that is, we fixed the number of success, and our question is, what is the probability value that he gives the fixed number of correct answer, that is third correct answer, in some, say, 5th attempted question or 10th attempted question. If that is the situation, we are finding the probability values like this. And one thing very important to note here, that is very, very clear also by the definition. Actually, when we are defining the negative binomial distribution, see, when we are defining the negative binomial distribution, our aim is x is the number of failures preceding r success. And that, so the probability of x is equal to x. We have the x plus r minus 1 cx, p power r, q power x, where x is equal to 0, 1, 2, 3, etc. and p plus q is equal to 1. So this is the probability mass function of the negative binomial distribution. Just think of this r success, r is equal to 1. So suppose r is equal to 1, what is the change? What is the modification in this case? So r is equal to 1 means it is x, that is 1. So p power 1, p, q power x. So when r is equal to 1, probability of x is equal to x is nothing but q power x into p, where x is equal to 0, 1, 2, 3, etc. So this is our geometric distribution. So that means negative binomial distribution is actually a general version of the geometric one. Or we can say that geometric distribution is a specific case of the negative binomial distribution. The negative binomial distribution, we are modeling number of failures, probability model of the number of failures preceding r successes. But in the case of the geometric distribution, we are modeling number of failures preceding the first success. So that is, when the suppose we have the negative binomial distribution, and if r is equal to 1, that reduces to the negative geometric distribution. So note that when r is equal to 1, our f of x is equal to q power x into p, where x is equal to 0, 1, 2, 3, etc., which is the probability mass function of geometric random variable. Hence, geometric distribution is a particular case of negative binomial. for concluding this definition and other things, one more thing we have to specify here. Earlier we have the probability mass function expression, that is f of x is equal to x plus r minus 1 cx p power r q power x. And that expression can be written in another form also. That is, negative binomial probability mass function can be represented in another form as f of x is equal to minus rcx p power r minus q power x. How it is possible? Because we have the f of x value x plus r minus 1 cx p power r q power x. This is our, of course, x is equal to 0, 1, 2, 3, etc. and p plus q is equal to 1. This is our probability mass function of the negative binomial distribution. Let me consider this, and this is equal to actually x plus r minus 1 into x plus r minus 2 into this is r plus 1 into r divided by x factorial, because when we have x plus r minus 1 cx is simplified, we have x plus r minus 1 factorial divided by x factorial into r minus 1 factorial. So, the common factor from here r minus 1 factorial and other factors will be cancelled, and so this is p power r q power x. See, so this and x plus r minus 1 cx is simplified, we have this value, and let me write this value as this is minus r into minus r minus 1 into etc. minus r minus x plus 2 into minus r minus x plus 1 into minus 1 power x. So, that is with all the factors, let me multiply minus 1, and to reduce that, that is minus 1 power x. This way you can write whole divided by x factorial p power r q power x. And this is nothing but, this is equal to, see, this is minus r minus 1 etc. up to minus r minus x plus 1 divided by x factorial, that can be written as minus r cx. This expression from here to here and this are combining, you can write that this is minus r cx, and minus 1 power x and q power x is combined, and so we have p power r minus q power x. So, f of x, that is equal to x plus r minus 1 cx p power r q power x, that is the original form of the probability mass function of the negative binomial distribution, and that can be written in another form minus r cx p power r minus q power x. We are writing this expression, this is minus r cx p power r minus q power x, x is equal to 0, 1, 2, 3 etc. up to etc. and p plus q is equal to 1, where p is a value in between 0 and 1. And already I have given the reason for representing that expression like this, that is the procedure. We have the simplification of that expression gives us the value. So, the negative binomial probability mass function can be represented in the another form of this form. And what is the meaning of this? This, see, minus rcx p power r minus q power x, which is the x plus 1th term of the expansion of this one. Or we have, suppose you have the f of x value, suppose you are considering over x is equal to 0 to infinity. This is equal to sigma x is equal to 0 to infinity p minus RCX p power r minus q power x, and that is equal to p power r is nothing related with the summation sigma x is equal to 0 to infinity minus RCX minus q power x. See, this is actually minus sigma x is equal to 0 to infinity minus RCX minus q power x, which is this is the expansion of 1 minus q or power minus r. So, this is f of x is equal to minus RCX p power r minus q power x, that can be considered as the x plus 1th term of the expansion of 1 minus q power minus r into p power r. So, that is this f of also one thing you can note here, this is p power r into this expansion is nothing but 1 minus q power minus r. So, that is p power r into this is 1 minus v, this is p power minus, this is 1. So, we have this expression, that is f of x is equal to 1 we have established here, and summation of the probability mass function is equal to 1, that is obtained by arguing like this. So, the negative binomial distribution probability mass function can be represented in different ways. One way of representing a probability mass function f of x is x plus r minus 1 c r minus 1 p power r q power x, where x is equal to 0, 1, 2, 3, etc. Or in another form, this is x plus r minus 1 c x p power r q power x, or minus r c x p power r minus q power x. In all the cases, the x random variable have the values 0, 1, 2, 3, etc. So, these are the different forms of probability mass function of the negative binomial distribution. And before concluding, this negative binomial distribution can be represented in another form also, that is the second version of the negative binomial distribution. Suppose we are interested in the distribution of the number of trials required instead of number of failures. Earlier, we have the model probability mass function value corresponding to probability of x is equal to x, where x is the number of failures preceding r successes. Suppose we are interested in the distribution of number of trials required to get r success, then you define the random variable y as the number of trials required to get r success. So, that is y number of trials required to get r successes. See, this is actually, if x, earlier x is the number of failures preceding r success, so this is actually x plus r. If y is the number of trials required to get r success and x is the number of failures preceding r success, earlier we have defined x as the number of failures preceding r successes and y as the number of trials required to get r successes, then y is nothing but our x plus r. And probability of x is equal to x, we have x plus r minus 1 c x p power r q power x. So what is probability of y is equal to y? This is our question. That is probability of getting y value is equal to y. That is, how do you find this? That is equal to y is our x plus r is equal to y. Probability of y is equal to y, that means probability of x plus r is equal to y, and that can be represented by probability of x is equal to y minus r. Probability of x is equal to y minus r means what? So we have probability of x is equal to y minus r. We are finding this. Earlier we have probability of x is equal to x as x plus r minus 1 cx p power r q power x. This is the expression we have. So what is this probability of x is equal to y minus r? This is x is y minus r plus r minus 1. So y minus 1 and x is y minus r. P power r and q power x, that is y minus r. So probability of, we started from probability of y is equal to y. So probability of y is equal to y is obtained as y minus 1 c y minus r p power r p q power y minus r, where y is equal to r, r plus 1, r plus 2, etc. So this is another version of the negative binomial distribution. So we can prove different properties of the negative binomial distribution in the next session. So we are wind up this session here. Thank you for listening this session. Thank you.